This lecture is going to be on probability theory and probabilistic reasoning, focusing on certain kinds of inductive logic. As we've covered up to this point in the course, valid arguments, are deductive arguments, and they're basically the best kind of argument that one can give without knowing all the facts, right? You can give premises, hope that those premises are true, and you can set the argument up in such a way that the conclusion is going to be guaranteed if the premises are true. But we usually don't have all the facts, or at least we're not certain of all the facts, right? And we usually don't get the right kinds of premises for all of the arguments that we want to make. So like conditional statements of the form if-then, depend on or are made true by certain relations out in the world of necessity and sufficiency. But those kinds of relations are ultimately limited, right? Like it's not like, everything is set up in such a way that, being some way is a necessary condition or a sufficient condition for being some other way. Sometimes certain things happen or are the ways that they are because of correlations or causations. And so sometimes, you come to know things merely on the basis of other forms of reasoning, not these technical, very philosophically rigid forms of reasoning that involve knowing whether or not something is a necessary condition or a sufficient condition for something else. So in order to kind of capture this other kind of reasoning, this other kind of argumentation, we need something beyond mere deductive reasoning abilities and valid arguments to kind of capture what it is to have a good or bad reason or good or bad argument for believing some particular thing without having premises that are necessary or sufficient to back up your conclusion, right? You want sometimes you want to have the ability to use weaker premises to support your conclusion, even if you don't have what we might think of as conclusive support, that is, that your conclusion is guaranteed. And two, at least, of the kinds of relations that often are you might think up here are things like causal relations and covariance. And so like a causal relation, right? You might take this kind of this type of argument seriously, right? If the wind blows very hard, then that tree branch is likely to break, right? So that's not a guarantee, right? The wind could blow pretty hard and maybe that tree branch will stay up there. But in this case, that seems like a pretty plausible conditional, but that conditional doesn't give you a necessary condition, right? It's not the case that if the wind, it must be the wind must blow very hard for the tree branch to break, right? The tree branch could just fall off on its own. It's also not a sufficient condition, right? It's not the wind blowing very hard is not sort of enough for the tree branch to break. There's got to be a lot of other there needs to be other features, other factors involved, right? Like that the tree branch is actually just hanging on by a thread. The causal relation here, though, that underlies the truth of this conditional seems like the kind of thing that we would want to appeal to for thinking something, right? Like if you were, doing yard work and you're like, well, I really don't want that tree branch to fall and break my window or something like that, then this is a good reason for going and cutting down that tree branch, right? Because you think, look, like, well, eventually the wind is going to blow and it might knock the tree branch off. So this is the kind of reasoning, this is the kind of relation or the kind of thing in the background that we might be appealing to when making a more inductive type of argument, going beyond merely a valid deductive style argument and into something that's just inductive. Similarly, covariance, right? So there's a co-varying relationship between air pressure and storms. In a way, there's a causal relation that's behind this, but it's hard to pin down exactly, and then it's not always the case that air pressure drops when a storm approaches, but most of the time, right? And the idea here is basically just to sort of say, look, like I mean, this is similar like cancer and smoking, right? Cancer we think causes smoking, but it's really hard to nail down the exact causal relation, like how the mechanism of smoking a lot eventually gets you to having lung cancer. But we do think that these things co-vary, and they co-vary so much that we have, plausible arguments that we can appeal to because of this covariance. And so, like the argument, like you shouldn't smoke because you will eventually get cancer from the smoking. Seems okay. And in this case, also, like if you're checking your barometer, if you see the air pressure drop really quickly, that means that the storm is coming in pretty fast. So different kinds of inductive reasoning can account for these kinds of inferences, and that's the kind of point here, is that deductive inferences can't account for these, like deductive reasoning, valid arguments, can't account for these kinds of inferences because they, need the premises to guarantee the conclusions, whereas there are some kinds of premises that just don't guarantee their conclusions, but they're really good still for what you believe, for determining what you should believe. Now, all inductive reasoning is inherently risky, just because it's possible on the basis of whatever your premise is to make an inference to a conclusion that ends up being false. Just a bit of terminology here, and what an inference is what one's doing, right? You're inferring. To make an inference is what you're doing when you infer one thing from another. So an inference is basically like an instance of reasoning where one comes to believe something or believe that something is likely based on something else. And inductive reasoning is basically in the business of making inferences about likelihoods, about whether or not something is probable, whether or not something is likely to happen. And inductive arguing is risky, right, in the sense that it's not always, whether or not something's likely to happen doesn't determine that it will happen, right? Just because something's likely, something could be 99% likely, but it could still, the 1% could still occur, right? Now, there's two different kinds of inductive reasoning that are worth kind of trotting out here. One is reasoning about what you should believe, and the other is reasoning about what you should do. Right? So up till now, we've kind of just been talking about what you should believe, and that involves, what reasons you have for taking some particular statement, or what we call a proposition, to be true. But there's also reasoning, especially in inductive cases, about what you should do, right? Most of the time when we're trying to decide to do something, we don't have certainty, right? We don't have deductive proofs that what we're going to do is definitely going to happen. What we're going to try to do is definitely going to, like, that we're going to succeed, right, in everything that we do. So reasoning about what it is that we're going to do, our actions, is almost always inductive in form. And reasoning about action, reasoning about what it is that you should do given your beliefs, your desires, and how the world is called decision theory. Decision theory studies the rules behind what we call maximizing expected payoffs, or maximizing utility. That's the phrase that economists and other people like to use for what it means to have a sort of expected payoff or a practical payoff. And when it comes to decision theory, you think in sort of these terms, right? You think like, well, look, if I decide to do this one thing, then there's a high chance, like let's say like a 90% chance of something else happening, Y, and a low percent chance, like a 10% chance of not Y, of Y not happening. But I want Y to occur, right? And so you need these things, right? You've got to like believe that if you do something, then something else will happen, and you've got to want that other thing to happen, right? And basically what this is called is it's means ends reasoning. So I desire for a certain end, I desire for a certain situation to occur, and then I recognize that there are certain means to take in order to achieve that end, and then I think about like, okay, how likely taking those means are to achieve that end. Like, if so just like right, I need some milk. I'm out, and I know that if I drive to the store, I'll be able to buy some milk, right? And then I'm thinking like, okay, well, it's pretty likely that the store is going to have milk, right? Their stores are rarely out of milk, and my car is pretty reliable. But it's always possible, like, there's a small chance that I drive my car breaks down, or like the store is out of milk because there's been some catastrophe or milk shortage or milk recall. You never know, right? But so that, and this is all goes into our forms of reasoning every day when it comes to making the decision for me to go get in my car in order to go get milk, right? Um, and Decision theory is really interesting and worth studying more, especially if you go on to do more philosophical thinking, or actually anything in like economics. And so it's good to know about, and basically the fundamentals of probability theory are tied up in decision theory. One of the great uses of decision theory is the prisoner's dilemma. So I suggest that you go watch the YouTube video on the prisoner's dilemma on Canvas. All right, now moving into direct discussion of probability. You might think like, okay, what is it for a decision or something to be fair between two options, right? Well, it's kind of hard to say. Like, it's hard to say what it is for someone to make a fair decision between two people, right? Because people always kind of have internal biases. But some things aren't biased, right? Some things are fair. And at the very least, it's not impossible to say what fairness is in probability theory. There's just a lot of kind of vague terms that are hard to make precise in like a mathematically precise way, but we can sort of show in a mathematical way what we mean by fairness, right? And what we mean by fairness more often than not is unbiased. A fair coin is going to be a kind of coin that is not biased. That means that the coin is not favoring either side when flipped, right? So you flip the coin and it comes up heads just as many times as it comes up tails. And then we understand bias in terms of tending to favor one side or one option rather than another or some set of others, right? So if you had like a loaded die, like in dice, right, that the bias would be not just say it comes up 6 all the time. It's biased towards 6 rather than 1 through 5. It's not just always a heads or tails type option, right? You can have bias with more than one option or two options. But the idea here is, something being not biased means that it doesn't tend to favor any particular side over another. And so now we can understand what fairness is in terms of understanding what bias is, and then saying fairness is just being unbiased. But we can also understand fairness in terms of this other property that we might call independence or dependence. And independence is probably best understood causally, right? Something is independent of something else if the first thing can't be affected by the second thing, or just isn't affected by the second thing. And or you might think that the second thing cannot influence the first thing, right? So one thing is independent of another if there's no influence relation between the one thing and the other thing. And here, right, you might think like, okay, so when it comes to a coin, a truly fair coin will be one that has a random set of outcomes when you flip it. And that's because, no previous flips of the coin influence the next flip of the coin. So the coin flips, each coin flip is independent of all of the previous coin flips. Sometimes, certain kinds of games, especially, the later outcomes are not independent of the previous states of the actual scenario, and we'll talk about this uh, more at length in a moment. But the idea here is that if you had a coin that for some reason like would tend towards coming up heads if it had come up tails the time before, well, then that wouldn't be an independent coin toss, right? It would be a dependent coin toss. There would be something worthy of taking account of, right? The history of the coin tosses in this case. It's similar to yeah, if you're playing a certain game and once something comes up, like you take it out of contention, right? Like you're rolling dice in like Yahtzee or something, and it's like, oh, okay, I got 3 6s. Well, now the next time I'm trying to not get 3 6s anymore, or something along those lines. Being biased is different from being from having independence, right? Being unbiased is different than being independent, and vice versa. And the thought here is basically just to sort of show that there are these two ways that something could be unfair, but they're different ways in which a thing could be unfair. So, like a biased coin could come up heads 55% of the time, but that doesn't mean that each of the coin tosses is somehow dependent on the previous ones, right? You could have a biased coin, but that doesn't make it the case that the previous coin tosses somehow affect the future coin tosses, right? So in this case, right, this is a long string of heads, tails, heads, heads, tails, 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 heads, tails, heads, right? It's a long string of somewhat random. You could have one of these where ultimately it like conclusively shows that heads is sort of 55% likely to come up, and tails is, but that's not going to change. Like once you get to the last one, like say the last flip is tails, that doesn't mean that the next flip is somehow affected. That it's more likely to be heads than 55%. It's just 55% because of the bias of the coin. So we still have independence, but bias. It's also possible for us to be in a situation where we lack independence. So like the future is dependent on the past in some sense, but while we don't have bias. So in this kind of game, you could have something that would, in a sense, be unfair in one way, depending on how the game is played, where we lack independence. So here's an example of an unbiased game where there's no sort of like bias here, but there is a form of dependence on what's going to happen. Imagine you have a bucket and it's got 4 different colored balls, 5 of each of those balls, right? So we got 20 balls in a bucket, 5 red, 5 blue, 5 yellow, 5 green. And now you take out one ball, right? And that ball is red. Okay. Now, what is the likelihood that the next ball that you take out is going to be a green one? Well, the initial likelihood that you would get a red ball is 1 in 4, right? 1/4, because there's 5 of each balls. But once you've taken one out, well, now there's less balls in the basket, right? And if there's less balls in the basket, then the odds have shifted, right? Now there's only 4 red balls, and so the likelihood of getting a green, blue, or yellow ball has gone up. And so unless you were to replace the initial red ball, the next the next choice of a ball is, in a sense, dependent. The likelihood of the next choice is dependent on the fact that you pulled a red one out before. So it changes the probability in this case, and so the actual likelihood of the second ball being taken out is different and so dependent. Understanding dependence is important because there's a specific kind of fallacy in reasoning that people often commit without sort of being aware of it. It's called the gambler's fallacy. And the gambler's fallacy is a fallacy of independence. It's basically a fallacy where you ignore independence when independence is actually there, right? You sort of imagine a dependence actually being there when it's not. So take the game of roulette. A roulette, for those of you that don't know, is basically this spinning wheel with a bunch of numbers, and each of the numbers is red or black, and then there's a couple of zeros on the board, usually two, that are green. And that basically, it's a difficult game to win if you're gambling. But a lot of people will just sort of, you can bet on red or you can bet on black. And that's sort of, if it comes up one way or the other, then you win, right? And assume that this roulette wheel is fair, meaning it's unbiased, right? None of the colors are more likely than the other. Except for, of course, the green is much less likely, but at the very least, insofar as each thing, none of the particular numbers is more likely than the other, and so each of them is red or black, and so ultimately, there's no way in which red or black is more likely. And all of the past spins have basically been in this sort of line, right? We've got red, 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 blue, blue, black, black, red, black, black, red, black, 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 red, 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 black, green, red, red, right? And then the end of the string, we've got like 6 or 8 blacks in a row, right? There's just like so many blacks all in a row. And then you're thinking, as the gambler, you've put money, you've got money to bet. You're like, okay, what's the most likely thing to come next? What's going to spin next? What color is going to come up next? If you thought that red was likely to come up next, you would have fallen victim to the gambler's fallacy. And why is that? Well, because whether or not red or black come up is totally independent of all of the previous spins, right? The gambler thinks, well, something like this, like, look, we've hit black the last 8 times in a row, so it's time to bet it all on red. It's, it's red's turn, right? Red's gonna come up. Red's gotta come up soon, right? But this is a fair roulette wheel, right? Each spin is independent of each other spin, and so the previous spins don't matter to the next outcome. Surely, eventually, red will come back up, given that it's a fair roulette wheel. If it never came back up, then I would be, highly questionable. I would think, actually, well, maybe this roulette wheel has gone skewed. It's become biased. But the likelihood that red's going to come up in the next spin is just as bad as it was in all of the previous spins, right? It's just as unlikely, and it's just as likely. There's no sort of new dependence that we've gained just on the fact that the past 8 spins were black. This leads us to probably the last bit of more technical material that we're going to actually cover in this class, and that's the basics of probability theory. So first of all, just some really basic ideas. In probability theory, some people talk in terms of situations, and some people talk in terms of propositions. A situation, when you talk about the probability of a situation, you think of in terms of like the probability that that situation will occur, will happen, right? Whereas a proposition or a statement, you say, the probability that some particular statement P or some proposition P is true or false. And this is just a way that people talk, but you can kind of translate back and forth between both of them, and I'll kind of go back and forth between both of them. In a way, right, talking about situations is more akin to talking about like decision theory, like when you're talking about when something is more likely to happen or what you should do. And proposition talk is more likely to come up when you're worried about like what you believe, like what you should think, right? Whether or not something is true or false. Now, we also need to introduce a kind of new set of notation in order to get by here. And it's pretty simple. Basically, the new notation is just something like, look, when you're talking about the probability of something happening, you just put a little PR or maybe even just a P, and then in parentheses after it, you put the sort of name that you've given to the event or the proposition, right? So here we have R, and PR parentheses R is basically just what we mean by the probability of the event R happening. Another thing to focus on is that we're going to like sort of use the letter E specifically to mean evidence. And then the sort of last thing is that we're going to use the backslash, and sometimes the book or other people will use what's called the vertical slash, which is just a straight line, but we don't have access to that on our keyboards sort of in an easy way. So just a backslash. And what a backslash means is given. So for example, if we have this sort of PR, so probability of R backslash E, that means the probability of R given E. And so you kind of could read that like the probability of the event R happening given the evidence that we have for R happening, that's E, right? Given a particular bit of evidence. There's a little bit of sort of math involved here. I'm sorry if you were taking this class hoping to never have to do any math, but it's not bad, and I'm not going to try to make you do too many problems that involve too much, mathematical reasoning beyond very basic mathematical reasoning. So one of them is sort of just more symbolism, right? When we have this symbol like the probability of A and B, well, the probability of A and B basically just means that the probability of A times the probability of B, right? Whenever you have two things, right, they are each less, like it's less, whenever you have two things happening, it's less likely that both of them will happen together, right? And so you have to multiply the probabilities, and then you end up with a smaller number. This is a sort of funny thing that like happens to people. I'll explain it in a minute. And then, so the probability of A times the probability of B, and then that also means exactly the same thing as just putting the probability of A next to the probability of B in the way, it just means that you're supposed to multiply those two numbers together. And then similarly, like we've got dividing probabilities, and dividing probabilities is you'll have like a line, you'll have one of the probabilities above a line and one of them below a line. And so the best way to sort of just show that here is just to use underlining. So I've just underlined one probability and then hit enter and put the other probability below it. And so here to divide probabilities, right, we've got the probability of A divided by the probability of B. And sometimes this will matter. One other thing to know is what's called conditional probability. And so that's what's going on with these slashes, right? And so the probability of P given Q, this is how you symbolize it, right? Probability P slash Q. And the basic idea here is just to sort of say like, sometimes certain things will go up, right? So take like the probability that I stub my toe today, right, at some point. Well, that's, there's a certain likelihood, right? I stub my toe every once in a while. But the probability that I stub my toe, given that I didn't wear shoes all day, right? Well, now the probability of P given Q, that's going to go up probably, right? If I was wearing shoes all day, I'm much less likely to stub my toe on that day than I am in the situation in which I stub my toe and I'm not wearing shoes, right? And so here, that's basically the idea, is that this is just a different way of describing the probability of a certain thing given some particular condition. Sometimes the probability given the condition will go up, and sometimes the probability given the condition will go down. Here's another really basic example of probability. Conditional probability, right? So take the probability of my rolling a dice and getting a 3, given that my roll was odd, right? Now, what exactly is going on there? Well, if I've got a fair 6-sided die, then, right, how like what's the probability of rolling a 3? Well, it's 1 out of 6, right? But what's the probability of my rolling something that was odd? Well, that would be 1 out of 2, right? Because there's 3 odd numbers and 3 even numbers on a dice. So what's going on here? Well, I've got the probability of 1/6 over the probability of 1/2, right? So the probability 1/6 given the probability 1/2. Well, guess what? If we divide 1/6 by 1/2, we end up with 1/3, right? So that would be what is it? 1/6 is like some weird like 0.16 something like repeating, and then 1/2 is 0.5, right? If you divide those, right, then you end up with 0.333 repeating, and you can always test this mathematically, or if you have a better time actually dividing with fractions. I'm terrible at this kind of math as well, but it's worth kind of just trying to get your head at least a little bit around it, where the idea here is, the conditional probabilities can be defined this way, where you can actually calculate, given the probability of one thing and the probability of the other thing, to give you the resultant probability. And this is right? This is exactly right. The probability of rolling a 3, given that my roll was odd, well, 1/6 and 1/2, right? Right, and so I end up with 1/3, because the probability of getting a 3 between 1, 3, and 5 is just 1/3. Here's something else that you can do, right? So the probability that coin flip is going to be heads, given that the last coin flip was heads, right? So what we got here is we're looking for the probability of a particular coin flip being heads, right? And the probability that the previous coin flip was heads. So both of those are going to be 1/2, right? And so now we've got the probability that the coin flip, so we've got 1/2 times 1/2, and that's ultimately going to be divided by 1/2. And 1/2 times 1/2 gets you 1/4, right? Because it's half of a half. And then 1/4 divided by 1/2 ultimately just brings you right back up to 1/2, right? And that's a sort of an interesting way to see that actually in this case, particularly with flipping coins, the probability of the previous case is totally independent of the probability of the next case, right? So given that you just flipped heads, right, the probability that the next one you flip is heads is still just 1/2. Now, this is different than the probability of flipping 2 heads in a row. And I want to just to make that clear, right? So there's a difference here between flipping a coin and it turning up heads, and then the next flip. Like, what's the probability of the next flip? Well, it's just 50-50 still, right? Whereas the probability of flipping 2 heads in a row, well, that's different. That's the probability of the first one times the probability of the second one. So that's going to actually be 1/4. And it's worth kind of getting clear on this. So people are often confused, and you can always kind of try. You can try this out with your friends. It's kind of funny. All right, so you tell your friends this story, right? Shirley, right, is a woman. She's pro-choice. She goes to rallies and marches for women's rights. She hangs out with a bunch of like-minded individuals, and they make signs and discuss ways to bring down the patriarchy, right? You tell your friends this story, and then ask them this question. All right, what is more likely? That Shirley works at a bank, or B, that Shirley works at a bank and is a Democrat? Now, the issue here is that a bunch of people are going to be pulled towards B being more likely because of the way that the story is set up. But the rules of probability are just so that anytime you have 2 things, it's always less likely than just having one thing, right? So, like, what's the likelihood that Shirley works at a bank? I don't know, like 1 out of 100 people maybe work at banks or something like that. But what's the probability that Shirley works at a bank and is a Democrat? Well, given this story, it seems likely that she's a Democrat, but that likelihood, maybe that likelihood is 75% in this case. Well, guess what? If it's 1 out of 100 and 75%. Well, now what you have to do in order to determine the probability of B, you have to multiply 1 out of 100 and 75 out of 100. And guess what? You're going to end up with an even smaller number. So just on the basic rules of probability here, anytime you have one thing happening, that's just going to be more likely, like objectively, than that thing and something else happening. Yeah. All right, and this brings us to a discussion of Bayes' rule, and this kind of begins the wrapping up phase of this discussion. So Bayes' rule, Bayesian reasoning is a form of probabilistic reasoning, and it's a way to update your beliefs using probability theory, particularly when you come to have new evidence. One thing that's worth pointing out here, we're introducing another letter, right? The letter H. The letter H here means hypothesis. The letter E still means evidence. And so Bayes' rule basically works like this. It says, and this is like a mathematical formula in a sense, like, and it just works out. It says that the probability of a particular hypothesis that you have given new evidence that you've gained, right? So the idea is like you have a theory about how the world works in some way, and you gain some new evidence, and now you're like, well, okay, what should my confidence be? What should I believe? Well, I need to know what the new probability is, and the new probability, the probability of your hypothesis given this new evidence, is equal to, and then this is the formula, right? The probability of the hypothesis itself times the probability of the evidence given the hypothesis, which is the reverse of the thing, all of that divided by the probability of the evidence itself. And this is a little bit confusing, but it's really helpful once you kind of get a hold of it. So again, let me go through it. The new thing that you're looking for, right, is the probability of your hypothesis, your theory of how the world works, given this new evidence that you've got, right? So your theory of how the world works comes, you see some new evidence and you're like, oh man, does that change my beliefs about this theory that I have? And the way that you can calculate that is you take the probability of the theory on its own, hypothesis that you have, and you multiply that by the probability of the evidence given that the hypothesis is true, right? And that can be a rather interesting number. Sometimes it's really likely, and sometimes it's really unlikely. And then you divide that whole thing by the probability of the evidence itself, that the evidence is correct. And let me give you some examples. So the base rate fallacy gets brought out here a lot because this is sort of exactly the kind of reasoning fallacy that you want to avoid, and that the Bayes rule helps you to see and avoid. And so it's basically like this, right? So take the hypothesis that you have. We'll just make up a disease, rare COVID, right? It's like some very, very interesting strain of COVID. And the evidence that you have is that you have all of the symptoms, right? You have all of the symptoms of rare COVID. And then the fallacy is ultimately that you should believe the hypothesis that you have rare COVID. And so let's explain this here. Now, how exactly does this all work? Well, the probability of the hypothesis, just to begin with, right? How many people get rare COVID? Well, it's like 1 in 1,000, right? 1 in 1,000 cases of COVID are cases of rare COVID, we'll say. And then we take the probability of the evidence, right? The evidence is, like you have all these symptoms. Well, the probability of the evidence is like 1 in 10, right? So 1 in 10 people that have COVID have all of the symptoms of rare COVID, right? So now we've got an interesting set of information, right? The hypothesis, 1 in 1,000 people get rare COVID, but 1 in 10 people get these symptoms when they get COVID. And so now, okay, so now we've got those two numbers, and now we've got this final one, the probability of the evidence given the hypothesis. Now, what exactly is going on here? The probability of the evidence given the hypothesis is, well, how likely is it that I have all of these symptoms, given that I actually have rare COVID? Well, that would be pretty high, right? So we're assuming that's like 95%. 95% of people that have rare COVID have all of these symptoms, right? So like that's just when you get it, you have these symptoms, right? Now, okay, so let's break these up again. The probability of the hypothesis that you have it is 1 out of 1,000 people that get COVID get rare COVID. The probability of the evidence, like having all the symptoms, right, is 1 in 10, right? So 1 in 10 people that get COVID have these symptoms, right? And then the probability of the evidence given the hypothesis. Well, the probability of the evidence, that the evidence being that I have all these symptoms, given that I have rare COVID, well, that would be 95%, right? If I basically, that just means like if I get rare COVID, I'm gonna have these symptoms. All right, well, now we can run our little Bayes theorem mathematical thing on it, right? We're just multiplying here. So what we have the probability of the hypothesis given the evidence is equal to, well, the first number, the probability of the hypothesis itself, multiplied by the probability of the evidence given the hypothesis. So that's going to be 1 in 1,000 multiplied by 95%, right? So 0.001 times 0.95. And then that number is going to be divided by the probability of the evidence itself, where the evidence itself is just the probability that I'm going to have all these symptoms, which is just 1 in 10. Well, guess what? When you do this calculation, the probability of the hypothesis given the evidence is very low. It's 0.0095. It's basically about 1 in 100, just below 1 in 100 people are going to. So ultimately, given this new evidence that you have all these symptoms, it's 1 in 100 people that actually have rare COVID, given all these symptoms in this situation. And this is why this is the base rate fallacy. It seems like it's really likely that you're going to have rare COVID if you have all these symptoms, but it's actually not, because people get confused when they think about the probability of the evidence given the hypothesis and the probability of the hypothesis given the evidence. There's a really big difference between believing that there's a 95% chance that you have this disease and that you have less than 1% chance of having this disease, right? And so you need to not confuse the base rate with the probability of the evidence given the hypothesis. That is, you need to not confuse, the base rate probability is basically the probability that you have this disease just given the fact that you have the evidence that you do. And in that case, it's literally 0.0095, which is ultimately just less than 1% chance. And the actual, what we would call the evidence given the hypothesis, which would be the probability of having all the symptoms that you have, given that you actually have the disease to begin with. These are two very different things. The probability that you have the disease, given that you have all the symptoms, is very low. The probability that you would have all the symptoms, given that you actually have the disease, well, that is actually quite high. And so oftentimes people confuse these two things. They take the probability that they're going to have all these symptoms given that they have the disease and think, oh, that's what I should believe, right? And so they're going to get worried in this case, right? They looked up on WebMD and they found out it's that they have all these symptoms, and they're like, oh my gosh, it's 95% chance that I have this disease, when actually it's 0.0095% chance, right? Or just less than 1% chance. It's a 0.95% chance, so they've confused the base rate for this other thing. Now, believing things just isn't always an all or nothing thing, right? We always have different levels of confidence in whether or not we think some particular thing is true or not, or will happen or not. And for this reason, the nice kind of thing is we can use probability theory and Bayes' rule to help determine what our confidence in a particular statement should be given our evidence and given our new evidence, right? The level of confidence that you have in a particular statement or that some particular thing will happen is called your credence in that statement or in that event. Now, in the base rate fallacy case, right, because you have the symptoms, you initially think that there's like a 95% chance that you have the disease, right? In that case, if that was true, then what your credence would be 0.95, right? We just talk about it in terms of decimal places instead of like percentages usually, but it's the same kind of thing, right? 0.95 out of 1. That's what you would be thinking if you thought, oh my gosh, the symptoms like nearly guarantee that I have the disease. But that's wrong. What we showed, right, is in the base rate fallacy case, you're confusing the evidence given the hypothesis for the hypothesis given the evidence. And once you get clear on those two concepts, what it is for something to be the evidence given the hypothesis versus what it is for something to be a hypothesis given some evidence, then you can realize that you can flip those. And your credence should actually be just 0.0095 in this case, which is less than 1%. And so, in fact, in this case, you should actually be highly confident that you don't have the disease, simply because the disease is very rare, right? It only happens in less than 1% of people that get COVID, even those people that get COVID that have all of the symptoms. Now, in order to sort of use Bayes' rule, basically what you do is you start off with your prior credence. You start off with your prior confidence in some statement or that some particular thing is going to happen. And then, given some new evidence that you come into contact with, either your confidence is supposed to, well, it'll go up or it'll go down or it'll stay the same. But you can use Bayes' rule to calculate or determine what the right level of confidence is. Now, we don't always have confidence sort of perfectly aligned in, we don't give the beliefs that we have like numbers, but we can sort of try, right? And usually you can sort of get at something like, well, look, I neither believe that it's definitely going to happen nor that it's not going to happen, or you could be like, I'm 75% sure, like I think it's more likely than not to happen, or I think I'm like 95% sure, like it's gonna happen, but there's that small chance that it would not. And so all of this kind of brings us home into being able to think kind of in this way. Like we can use these tools to do certain kinds of reasoning. Suppose, so I drove my car to the lot this morning and I left it there. And this is my prior credence, right? So like right now, I'm 95% sure that my car is in the lot, right? Maybe I'm even more than that because, nobody's breaking into cars these days, and it's very likely that my car is in the lot. But then I come across some new evidence, right? Like I open up my email and oh shoot, somebody from like HR or the facilities staff sent me an email saying, hey, this lot is going to be resurfaced. And I'm like, oh no, like that's the lot that my car is in. So I come across this new evidence. And now the question is like, okay, well, what should I come to believe in this case? Well, what I can do is try to determine what my hypothesis is given this new evidence, right? And that's going to shift, right? So my prior probability was like 95% sure that my car was in the lot. Well, now my new hypothesis, my new probability, given that I've got this new evidence, well, it's going to change, right? So the hypothesis, the hypothesis that my car is in the lot, given this new evidence that the car, that the lot is being resurfaced, it's going to drop, right, drastically. So now the statement that we're interested in, right, is whether or not my car is still in the lot given that the lot is being resurfaced. And the probability there, or the sort of confidence that I have in that, is like 0.25, right? So like under 50 means like I'm I'm confident that it's being towed, right? I have like this tiny like inkling of a hope that the thing is still there, but but now I'm more sure that it's towed in some sense. But yeah, basically what's going on here, and you're kind of doing this all the time in your head, and you don't always really know. But I'm following Bayes' rule here. I'm determining I'm taking my prior probability in a certain claim, and I'm thinking about it in terms of what's going to happen, right? So like, here's my initial claim: my car's in the lot. Well, and then there's the claim of like the evidence given the hypothesis, right? So like, what's the evidence given the hypothesis? That would be a situation in which the road is being paved, and my repaved, or the surf resurfaced, and my car is still in the lot. Well, that's going to be pretty close to zero, right? Why? Because, well, my car couldn't be there if they were resurfacing the thing, right? So the E/H is going to be super low. And so, 0.95 times something really low, like 0.05, that's going to give me some really low number. And then that ultimately divided by the probability that, they're actually currently doing the resurfacing. Well, maybe that's only like 0.75% sure because maybe they haven't started yet. Well, whatever that is, ultimately, all of that together is going to drop my credence, my confidence in whether or not I believe that my car is in the lot, down to a very measly small amount.